How barn builders designed pole barns to survive tornadoes and blizzards. There's something about an old barn standing alone in a field that captures the American imagination. Maybe it's the weathered wood, the faded paint, or just knowing that structure has witnessed generations of farmers working the land beneath endless skies. But have you ever stopped to wonder how some of these barns have managed to survive decades of nature's worst fury, while newer buildings crumble around them? Today, we're diving deep into the ingenious engineering behind pole barns and how rural builders across America's heartland develop techniques to help these structures withstand tornadoes, blizzards, and everything Mother Nature could throw at them. What we're about to uncover isn't just about wood and nails, it's about generations of hard-won knowledge passed down from father to son, tested by countless storms, and refined through trial and error in communities where your barn wasn't just a building, it was your livelihood. Let's start with understanding what exactly a pole barn is, and why this particular design became so prevalent across rural America. Unlike traditional barns built with conventional foundations, pole barns use a fundamentally different approach. Long wooden poles, typically 8 to 12 feet or even deeper, are sunk directly into the ground and embedded in concrete. These poles serve as both the foundation and the primary structural framework. The concept seems almost too simple, but as we'll discover, this simplicity is precisely what gives pole barns their remarkable strength. The history of pole construction in America actually stretches back further than most people realize. Native American tribes had been using pole-based structures for centuries before European settlers arrived. The teepee, perhaps the most recognizable example, used a pole framework that could withstand high winds on the open plains. When European settlers moved westward in the 1800s, they brought their own building traditions, but quickly learned that conventional European building methods weren't always suited to the extreme weather conditions of the American Midwest and Great Plains. Early American barns were typically built using post and beam construction with stone foundations. These were solid structures, but they required significant time, materials, and skilled labor to construct. As settlers pushed further into territories where timber was scarce and harsh weather was common, they needed something faster to build and more economical. The evolution toward pole barn construction accelerated dramatically in the early 20th century, particularly after World War II when new pressure treating technologies became available. The real breakthrough came when builders recognized that deeply embedded poles could provide exceptional resistance to the two forces that destroy most structures during extreme weather: uplift and lateral pressure. Think about what happens during a tornado. Winds don't just blow against a building from the side. They create a complex system of pressures, including devastating uplift forces that can literally rip a roof off or overturn an entire structure. Traditional buildings with shallow foundations are particularly vulnerable to these uplift forces. Pole barn builders in tornado-prone regions developed their techniques through observation and painful experience. After major tornado outbreaks, farmers and builders would survey the damage, noting which structures survived and which didn't. They noticed that buildings with deeper embedment withstood storms better. They observed that certain roof pitches performed better than others. They discovered that the way the roof connected to the walls made an enormous difference in whether a barn survived intact or was scattered across the countryside. Let's talk about those poles themselves, because the depth and installation method are absolutely critical. In the Midwest, where tornado frequency is highest, experienced builders insisted on embedding poles at least 4 feet deep, with many going 6 feet or deeper in areas with high wind exposure. But it wasn't just about depth. The bottom of each pole was typically set in concrete, creating what engineers call a moment-resisting connection. This concrete collar anchored the pole firmly, while allowing the natural flexibility of the wood to absorb and distribute stress during high winds. The type of wood mattered too. Cedar and black locust were prized for their natural rot resistance, but these weren't always available. As pressure treating technology improved in the mid-1900s, southern yellow pine became the material of choice. This lumber was abundant, strong, and when properly treated with preservatives, could last for decades, even when buried in the ground. Farmers in the Dakotas, Nebraska, and Kansas learned to specify poles with a minimum diameter of 8 inches, and often 10 or 12 inches for larger structures or in high-risk areas. Now here's where the engineering gets really interesting. The spacing between poles wasn't arbitrary. Builders developed rules of thumb based on the expected snow loads and wind pressures in their regions. In the northern plains, where blizzards could dump multiple feet of snow, poles were typically spaced 8 to 12 feet apart to adequately support the roof load. But in areas with higher tornado risk and less snow, poles might be spaced differently to provide optimal wind resistance. The roof design was equally crucial. Experienced barn builders knew that a roof pitch between 412 and 612, meaning the roof rises 4 to 6 inches for every 12 inches of horizontal distance, provided the best balance for most conditions. This pitch was steep enough to shed snow effectively, preventing dangerous accumulations that could collapse the roof, but not so steep that wind could get underneath and create catastrophic uplift. Speaking of uplift, this is where we see some of the most clever engineering. The connection between the roof trusses and the poles had to be absolutely bomb-proof. Traditional barns often used simple nailed connections, but pole barn builders in storm country developed much more robust methods. Heavy-duty metal brackets, through bolts, and multiple connection points became standard. Some builders used a technique where the roof trusses were actually notched into the poles themselves, creating a mechanical connection that couldn't simply pull free. The roof covering material also played a significant role in survivability. Early pole barns used wooden shingles or sheet metal. Metal roofing became increasingly popular because it was lighter than shingles, reducing the overall load on the structure and more resistant to fire. But metal roofing had to be properly fastened. Builders learned through hard experience that roofing screws had to be specifically designed for high winds, with special threads and washers that would grip firmly, even as the metal expanded and contracted with temperature changes. Let's talk about the walls, or rather, the lack thereof in many cases. Traditional pole barns often had minimal or no wall sheathing between the poles. This open-air design wasn't just about saving money. It actually provided significant wind resistance benefits. When a tornado or severe straight-line winds hit a fully enclosed building, the structure essentially becomes a box trying to contain enormous air pressure. Windows blow out, doors fail, and suddenly the building is pressurized like a balloon. The roof lifts off, walls collapse outward, and the entire structure fails catastrophically. Pole barns with open sides allowed wind to pass through rather than building up pressure. Of course, this design wasn't suitable for all purposes. Barns housing livestock or storing hay needed protection from the elements. Builders addressed this with various solutions. Some used horizontal wooden boards with gaps between them, allowing air movement while providing weather protection. Others used a combination of solid walls on the windward sides and open or partially open walls on the lee sides. When full wall enclosure was necessary, experienced builders knew to provide adequate ventilation through carefully placed vents and openings. They also reinforced the walls with diagonal bracing, essentially creating triangulated structures within the wall frames. Triangles are inherently stable shapes, and this bracing helped walls resist the racking forces that occur when wind pushes against a building from the side. The importance of proper bracing cannot be overstated. In the rafters and roof structure, cross-bracing served multiple functions. It prevented the roof from shifting laterally during high winds, it distributed loads more evenly across the structure, and it added torsional rigidity, meaning the building was less likely to twist under uneven loading. Builders in Tornado Alley often added extra diagonal bracing in an X pattern between poles, creating a framework that could flex without failing. Now, let's discuss blizzards, because the engineering challenges are quite different from tornadoes, though equally significant. The northern Great Plains regularly experience blizzards that dump multiple feet of snow accompanied by high winds. These conditions create several distinct threats to structures. First, there's the sheer weight of accumulated snow. Fresh powder snow weighs relatively little, perhaps 7 to 8 pounds per cubic foot. But as snow sits on a roof, it compacts and can absorb water, dramatically increasing its weight. Wet, compacted snow can weigh 50 pounds per cubic foot or more. A large barn roof covered in just 2 feet of wet snow could be supporting tens of thousands of pounds of additional weight. Builders in blizzard country designed their pole barns with this reality in mind. The roof trusses were engineered with adequate strength, often using larger dimension lumber than would be necessary in milder climates. The spacing of the trusses was calculated based on expected snow loads. In the upper Midwest and northern plains, trusses might be placed every 2 feet instead of the 4-foot spacing common in areas with lighter snow loads. The roof pitch we mentioned earlier becomes critical for snow management. A steeper pitch encourages snow to slide off before dangerous accumulations can develop. However, there's a catch. When large amounts of snow suddenly release from a roof, they can damage lower structures, bury livestock pens, or create other hazards. Experienced farmers often installed snow guards or used deliberate roof designs that controlled where and how snow would shed. Blizzards create another serious threat through wind-driven snow infiltration. Even tiny gaps in a structure can allow fine snow to penetrate, driven by high winds. Once inside, this snow accumulates, melts, refreezes, and can cause structural damage or ruin stored crops and equipment. Builders addressed this through careful attention to sealing and overlap details. Metal roofing panels were overlapped generously and sealed. Any openings for ventilation were designed with baffles or louvers that prevented direct snow penetration while still allowing air movement. The ground freeze-thaw cycle in northern climates created yet another engineering challenge. When water in the soil freezes, it expands, creating forces that can literally push poles upward out of the ground, a process called frost heaving. Builders countered this by embedding poles below the frost line, which varies by region, but can be 4 feet deep or more in the northern states. The concrete footing at the base of each pole had to extend below this frost line as well, anchoring the pole to soil that wouldn't freeze and expand. Let's examine some specific historical examples that illustrate these principles in action. In 1975, a series of devastating tornadoes tore through Nebraska and Kansas, part of what became known as the super outbreak season. Weather researchers who surveyed the damage noted that while many conventional buildings were completely destroyed, a significant number of pole barns survived with only minor damage. The barns that survived best shared common characteristics: deep pole embedment, robust roof-to-pole connections, and either open sides or well-braced enclosed sides. Similarly, during the historic blizzards of 1978 and 1979 that paralyzed much of the Midwest, many pole barns successfully weathered conditions that collapsed other structures. Farmers reported that their pole barns, some of which were decades old, handled snow loads that destroyed newer buildings constructed with different methods. The flexibility of the pole barn design allowed the structures to deflect and distribute loads without catastrophic failure. This flexibility is actually one of the most important but least understood aspects of pole barn engineering. Modern building codes and engineering calculations often assume rigid structures, but the old-time barn builders understood something more subtle. A completely rigid structure subjected to extreme forces will eventually reach a breaking point and fail suddenly and catastrophically. A structure with some flexibility can bend, absorb energy, and often survive forces that would destroy a rigid building. The wooden poles and the connections between components provided this flexibility. During high winds, the entire structure could sway slightly, absorbing and dissipating energy. The wood itself had natural damping properties, meaning it could absorb vibrations and stresses without transmitting them directly throughout the structure. This is why a pole barn might appear to be shuddering and groaning during a severe storm, but remain standing, while a more rigid structure nearby might suddenly disintegrate. There's also a fascinating social and economic dimension to how pole barn building knowledge spread across rural America. Unlike urban construction, which increasingly relied on professional architects and engineers, rural barn building remained largely a craft trade passed through informal networks. A farmer building a barn might consult with neighbors who had successfully built their own structures. Local lumber yards became repositories of regional building knowledge, with staff who could advise on appropriate designs for local conditions. Agricultural extension services, established by the land-grant university system, played a significant role in disseminating improved building techniques. Extension agents collected information about successful building practices and distributed plans and guidelines to farmers. After major storms, these agents would conduct damage surveys and publish findings about which building methods and materials performed best. This collaborative approach to developing building knowledge meant that improvements spread relatively quickly through farming communities. When someone discovered that a particular connection detail or bracing pattern improved storm survival, word would spread through the community and other builders would adopt the innovation. This decentralized, empirical approach to engineering may lack the mathematical rigor of modern structural engineering, but it was remarkably effective at producing buildings suited to local conditions. The materials and tools available in different eras also shaped pole barn designs. In the early and mid-20th century, most connection work used nails, lag screws, and simple metal brackets. The advent of better fastener technology in the 1960s and 1970s, including specialized structural screws and engineered connectors, allowed builders to create stronger connections more easily. The development of pressure-treated lumber meant poles could be reliably embedded in the ground without rotting within a few years, making the entire pole barn concept much more practical. Interestingly, modern engineering analysis has generally validated the empirical approaches developed by traditional barn builders. When engineers use computer modeling to analyze the stresses and forces in pole barn structures during extreme weather, they find that the proportions, spacing, and connection methods developed through trial and error closely match what engineering calculations would recommend. This speaks to the practical wisdom accumulated over generations of building and rebuilding after storms. It's worth noting that pole barn construction has evolved significantly over the decades, but the fundamental principles remain the same. Modern post-frame construction, as it's now often called, uses engineered lumber, sophisticated metal connectors, and synthetic materials that weren't available to earlier builders. Computer-aided design allows precise calculation of forces and required structural elements, but the core concept of deeply embedded poles supporting a flexible, well-braced structure remains unchanged because it works. There are, of course, limitations to what any structure can survive. No building technique can guarantee survival against a direct hit from an EF5 tornado, with winds exceeding 200 miles per hour. The most violent tornadoes produce forces that will destroy virtually any above-ground structure. Similarly, extreme blizzard conditions, with massive snow accumulations or ice storms that coat structures with hundreds of pounds of ice, can overwhelm even well-designed buildings. However, the vast majority of tornadoes are EF0 to EF2, with winds below 135 miles per hour. Most blizzards, while severe, produce snow loads within the range that properly designed structures can handle. The pole barn techniques we've discussed were developed to maximize survival rates against the weather conditions that farmers would most commonly encounter, and in this, they've proven remarkably successful. One aspect of pole barn resilience that deserves special mention is the distributed load path. In structural engineering, the load path describes how forces travel through a structure, from where they're applied ultimately into the ground. In a pole barn, multiple parallel load paths exist. Force on one part of the roof can be distributed through the truss system, down multiple poles and into the ground. If one connection weakens or one component fails, other elements can compensate, at least temporarily. This redundancy contributes significantly to survivability. The aesthetic simplicity of pole barns can be deceptive. To someone unfamiliar with structural engineering, a pole barn might appear crude or primitive compared to a conventionally framed building. But this apparent simplicity conceals sophisticated engineering principles working in harmony. Deep foundations resisting uplift and overturning, flexible materials absorbing and distributing stress, appropriately pitched roofs shedding snow and resisting wind, robust connections holding components together under extreme loads, and redundant load paths providing backup when individual elements are stressed. As we look at the rural American landscape today, we can still see countless examples of pole barns that have served faithfully for 50, 60, or even 70 years. These structures have sheltered livestock through countless blizzards, protected harvests through tornado seasons, and provided essential workspace for the families that built them. Many have required repairs over the decades, certainly. Roofing materials have been replaced, poles occasionally need reinforcement, and wallboards get replaced. But the basic structure endures. This endurance represents more than just good engineering. It represents the accumulated wisdom of generations of rural Americans who couldn't afford for their buildings to fail. When your barn houses your livestock, stores your feed, and protects your equipment, its survival during a storm isn't an academic question. It's the difference between making it through the winter or facing financial disaster. This practical necessity drove the continuous refinement of building techniques until communities developed methods that reliably worked. There's something deeply American about this entire story. It combines practical problem-solving, learning from experience, sharing knowledge within communities, and continuously improving through iteration. These weren't government-mandated building codes or solutions imposed from above. They were organic developments emerging from the real-world needs of working people, tested against nature's harshest conditions, and refined until they worked reliably. Today, professional post-frame construction companies build pole barns using engineered plans, manufactured components, and professional installation crews. These modern buildings benefit from computer-aided design, sophisticated materials, and decades of accumulated engineering knowledge. But they're built on foundations, literally and figuratively, laid by generations of farmers and rural builders who figured out how to construct buildings that could survive on the American plains. The next time you drive through rural America and see an old barn standing in a field, take a moment to appreciate the engineering wisdom represented by that structure. Those poles sunk deep in the ground, that roof pitched to shed snow, those bracing members preventing racking, those connections holding components together. Every element represents learned knowledge, tested against tornadoes and blizzards, refined through experience, and proven over decades. These barns are monuments to practical engineering, American ingenuity, and the resilience of rural communities. They remind us that sophisticated engineering doesn't always require complex mathematics or modern materials. Sometimes it requires careful observation, willingness to learn from failure, and the accumulated wisdom of people whose livelihoods depended on getting it right. The story of pole barn engineering is ultimately a story about people working with nature rather than against it. These builders recognized that they couldn't prevent storms, couldn't stop snow, couldn't eliminate wind. But they could design structures that flexed with the wind, shed the snow, and remained standing when the storm passed. They could build in ways that worked with the natural properties of materials rather than fighting against them. And they could create designs that had proven themselves across generations and countless storms. That legacy continues today. Modern post-frame construction has expanded far beyond agricultural applications. Residential buildings, commercial structures, and recreational facilities increasingly use post-frame methods, especially in areas with challenging weather conditions. The principles pioneered by rural barn builders have found applications far beyond their original context, proving once again that good engineering principles have lasting value. As climate patterns change and extreme weather events become more frequent in many areas, the lessons learned from pole barn construction become increasingly relevant. The resilience built into these structures, the attention to local conditions, the understanding of how buildings interact with wind and snow, all of these considerations matter more than ever. Modern builders and engineers would do well to study the empirical wisdom accumulated by generations of rural builders who had to get it right because failure wasn't an option. Thank you so much for watching this video. We hope you've gained a new appreciation for the engineering wisdom built into those barns you see dotting the rural landscape. If you found this fascinating, please hit that like button, subscribe to our channel for more deep dives into American history and engineering, and share this video with anyone who loves learning about how things are built and why they work. This video is inspired by real facts and historical developments and is not intended to represent or offend any person or group. The story of pole barn construction belongs to all the farmers, builders, and rural communities who developed these techniques through hard work and practical experience.